Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the basic concept of boundary layer. In the previous lecture, we had discussed about potential flow. Now, in this lecture, we will discuss about a very important concept of boundary layer, which is associated with viscous flow. Let us draw a flat plate, and we are showing it in a hatched manner to indicate its cross section, and the flat plate has a sharp leading edge. We will put our Cartesian coordinate system with the origin at the leading edge of the plate. Now, a uniform flow is approaching this flat plate. When the flow occurs over the flat plate, a very thin layer containing viscous effects, you can see that a thin region is formed over the flat plate. This region could be really thin, but we are showing it in a much more zoomed manner, that is why it looks thicker. So, there is a thin layer formed on the flat plate, where the viscous effects are significant. That means, the viscous stresses that we have learnt about, they all become very active within this layer. Additionally, this free stream flow, which is moving past the flat plate as well, comes to a standstill when you look right on the surface of the plate. So, on the surface of the plate, the velocity of the flow is equal to 0. Now, this is a problem in x y plane. Therefore, the velocity being 0 basically means that both components u and v will go to 0. This is what we call as the no slip condition. Now, the region of the flow which is within this viscous dominated layer is called as the inner flow, and that which is outside is called as outer flow. Now, the boundary of this region that we have drawn is basically a hypothetical boundary. On what basis have we defined this boundary? We say that whenever the free stream component of the velocity reaches about 99% of u infinity, then we will consider that as the edge of the boundary layer. So, the velocity will vary in a manner like this, and you notice that higher gradients of the velocity are noticed close to the wall and lower gradients as we approach that hypothetical boundary. And the thickness of this region is usually indicated by delta. That is what is called as boundary layer thickness. Mathematically, we would say that when u tends to u infinity at y tending to infinity, we have the edge of the boundary layer. But for all practical purposes, we consider it to be 99% of the free stream velocity. Now, it is obvious that by the time we reach the boundary, we have the condition of vanishing shear. Why vanishing shear? Because tau x y is the shear stress in this plane, which is of importance, and that is dependent on two terms. One is del u del y, another is del v del x. Typically, this term is a small term, but this is a significant term because very large change in velocity from a value of 0 to nearly u infinity occurs within a very short distance, that is delta, and therefore, the ratio is large. So, as this gradient becomes very small, that is when the velocity is changing very gradually, typically in the outer extent of the boundary layer, we say that we have reached a region where the shear stress is vanishing. The free stream Reynolds number for the free stream velocity that we have can be typically defined as, say, rho u infinity times, say, characteristic length scale of the problem by mu infinity. And we state that first of all, the boundary layer thickness is much smaller than the characteristic length scale, which could be the length of the plate, and on the other side that the Reynolds number is very, very large. So, when we look at 1 by Reynolds number, that is a small quantity. Remember that this is a quantity which is associated with the viscous stresses in the Navier-Stokes equations. We looked at an outer flow which is basically a potential flow region. Which is irrotational in nature, while the inner flow region is a viscous flow region, and it is also rotational in nature. That is because, as you may recall, that in this plane we can only have the omega z component of vorticity. So, when you look at the definition of omega z, as we said that this term is a small term, but the del u del y term is quite large. Therefore, omega z is not equal to 0, and therefore, the flow is rotational in nature within the boundary layer. Ludwig Prandtl of Germany had first seen the presence of this very thin viscous dominated layer through wind tunnel experiments, and then he proposed the boundary layer theory based on what is called as an order of magnitude analysis of Navier-Stokes equations. Here we are discussing about laminar incompressible boundary layer. In general, boundary layers could be existing in a turbulent incompressible regime. They could also be existing in a compressible regime where it can be again either laminar or turbulent. But the simplest case is that of laminar incompressible boundary layer, and Ludwig Prandtl basically dealt with Navier-Stokes equations in that sense and simplified it to give rise to the boundary layer theory accompanied with the boundary layer equations. So, the order of magnitude analysis of Navier-Stokes equation basically looks at the estimates of different terms in the Navier-Stokes equations and work out whether they are large or small. For example, if you look at a term like del u del y, which we have been discussing about, then the order of the term is typically like this, that it changes from 0 to u infinity within a distance of delta. Therefore, it is of order u infinity by delta, and therefore, since delta is a very small term and u infinity is a fairly large term, therefore, this happens to be a large term. Accordingly, the other terms are assessed and some of them are found to be of the same order, some of them are found to be much smaller than that. So, the very small ones could be represented like order epsilon, that means a small term. In this manner, Ludwig Prandtl did a detailed analysis and found that many terms in the boundary layer equations could actually become insignificant, and therefore, he proposed a set of equations which are now famously known as the boundary layer equations. And remember that his theory caters to the laminar incompressible boundary layer here. Later on, it has been extended to compressible situations and also by accounting turbulent effects. Notice that here we have dropped the unsteady term in the x momentum equation, and then we have dropped the second derivative of u with respect to x in the viscous terms. That is as far as the x momentum is concerned. As far as the y momentum is concerned, the result is very simple, del p del y equal to 0. That means, along the thickness of the boundary layer, there is no change in pressure. If that is the case, then pressure becomes purely a function of x, that is the streamwise location, and thereby this derivative can as well be represented as dp dx, an ordinary derivative instead of partial derivative. There is further implication of this in the sense that the fact that pressure does not change as we move along this thickness would mean that whatever pressure exists at this x location in the potential flow region will be felt all through the boundary layer right up to the wall. And that basically means that you can work out the pressure in the potential flow region by using Bernoulli's equation and that can be impressed within the boundary layer from the outer flow. That means, for the pressure we do not really need to look at the viscous equations. So, we had looked at the issue of magnitudes of different terms, whether they are very weak terms or strong terms which could be retained, and accordingly the boundary layer equations are proposed. So, a very important finding is in terms of the pressure, that the pressure does not have a y derivative within the boundary layer. Later, another very famous scientist, Blasius, found out self-similar velocity profiles within the boundary layer. What this means is that when we look at the velocity profiles at different locations in a boundary layer, we have to remember that at the edge of the boundary layer, at every location they are going to reach to the same free stream velocity, but that change is occurring over different distances. Therefore, if we look at it in the xy plane, these velocity profiles would look different, but if we look at a transformed plane by using certain scaling functions, then all these velocity profiles could be collapsed into a single profile and made congruent. That is basically the principle of self similarity. So, appropriate scaling functions were evolved or invented by Blasius, and that reduced the problem to that of solving an ordinary differential equation. So, instead of solving two partial differential equations, one is the continuity equation and the other is the x momentum equation with the simplifications proposed by Prandtl, a single ordinary differential equation would define the property variations within the boundary layer. We are mostly interested with how u changes as a function of y, and Blasius in the transformed plane solved it as a function of eta, which is nothing but y by delta, the ratio of y by delta. And then solutions evolved by Blasius are now available in the form of tables, from where you could read the values and use the Blasius solution for performing boundary layer calculations. So, this was another major development in the theory of laminar boundary layers. We were talking about laminar incompressible boundary layers more specifically. So, all this while we are mainly talking about the incompressible boundary layer, but we briefly mentioned that at high speeds the boundary layers will become compressible, and we have discussed in previous lectures that the v square by 2 term becomes a very dominating term in high speed flows. And as a consequence, what happens is that a large kinetic energy is dissipated within the boundary layer by the time the velocity reaches zero at the wall. Now, what happens as a consequence? There is significant rise in internal energy. That means, the temperature of the gas would rise significantly. This is one of the major factors which distinguishes compressible boundary layers from incompressible ones. Let us go back to some more on incompressible boundary layer, and we will draw from Blasius solution. What will we draw? We will draw some very important results. So, we are not going into the formal proofs because of paucity of time, but we will nevertheless make use of some of the findings of Blasius solution. we are first looking at an expression for shear stress at the wall at a location x from leading edge of the flat plate. So, from the table of values from Lassier's solution, the expression for the shear stress for laminar incompressible boundary layer comes out to be this. Remember that Rex is basically the local Reynolds number. That means, at a distance x from the leading edge, if you calculate the Reynolds number, then that is what it comes out to be, Rex. It is based on this length scale. Based on the tau value that we have, the local skin friction coefficient is what? First of all, it is represented like this. It is basically a non-dimensional form of the local shear stress. If you substitute the values, it turns out to be this. This is the local skin friction coefficient. Now, as you can understand, the local skin friction coefficient is a function of x, and if you were to find an average value of local skin friction over the entire plate, that means, let us say the total plate length is L. If you cover up to the length of the plate, then what is the total frictional force? Per unit span or depth, that means out of the plane of the paper. If you consider unit length, then you basically integrate the expression for tau w over the entire length of the plate. And what does it work out to be? If you integrate, you will find that it comes out to be this expression. Now, based on that, you can have an average skin friction coefficient on which we put an overbar. And what do? We basically divide this capital F by half rho infinity u infinity square L. And that comes out to be this, where REL is based on the plate length. So, where did we start from? We all started from here. That was the one expression where a value was taken from the Lassier solution, and that is where from we could derive all these expressions. Now, we already said before that u by u infinity that approaches a value of 1 as y tends to infinity. But for practical purposes, it is customary to select the boundary layer thickness as delta at a point where u by u infinity is approaching a value of 0.99. And if you go by that value from the Lassier's solution, you can show that the distance at which it occurs is given by this expression 5x by root over Rex. So, this number 5 again comes up from the Lassier's solution. So, delta is approximately 5x by root over Rex. Now, remember that root over Rex is what? It is root over x into rho infinity u infinity by mu infinity. So, if you do a x by root R e x, then it boils down to root over x into under root mu infinity by rho infinity u infinity, which means that when you go back to this expression delta, delta must be proportional to square root of x. That means, delta increases with distance by following this law. Now, why should the boundary layer grow? Now, the growth of the boundary layer is related to the momentum transfer from the plate surface through the no slip condition to the outer extent of the boundary layer. Through the action of viscosity, because viscosity assures this momentum diffusion. That is why, as we move down the length of the plate, we see more and more momentum diffusion and therefore, growth of the boundary layer. In the context of boundary layer theory, it would be very inappropriate not to talk about the concept of displacement thickness, which is represented as delta star, and it is defined as the distance by which the external potential flow is displaced outwards as a consequence of the decrease in velocity within the boundary layer. The streamlines are deflected because of this effect. So, if you look at the typical velocity profile in the boundary layer, let us say we are able to recover 99% of the free stream within this thickness. This region, which is lying beyond the velocity profile, is the region of velocity deficit. So, in this region, the u infinity minus u is greater than 0. We will take up the remaining part of the displacement thickness in the upcoming lecture. So, in this lecture, we briefly discussed about the basic concept of boundary layer flow, and we have talked about the main findings from Prandtl's boundary layer equations and Blasius equation, and in the subsequent lecture we will discuss further on the displacement thickness. Thank you.